In this video, I'm going to look at an R script. That R script is going to read in some data from an Excel file that's on the web. Then it's going to plot that data. That data is for a peak. So there's some chemicals, some processes done. That process, which is an absorption spectrum, has a peak, and we're going to fit it, the math, to a form that corresponds to peak, called the Lorentzian. It has three fitting parameters. It is like a nonlinear fit, so we're going to use the NLS in R, the nonlinear least squares method. And then we're going to make a plot with the fit and see if it's good. And then we're going to sort of restrict some of the data using subset and see what changes that makes to the fitting parameters. So let's get started. All right, so I'm going to use the open.xlsx library. So I'm bringing that in. If it's the first time, you'll have to install it. You'll get a little, if you're in RStudio, you get a little warning up here to install it. I have it installed. Okay, and then I am going to use read.xlsx. Here is, I think I will post this code in a comment, but here is a URL for this data. I didn't take this data. It came from, I have been using this data for years, but it came from a colleague of mine in the chemistry department, George Salub. And this data is on the first sheet of that Excel. So I'm specifying that it's sheet 1. Okay. So let's do that much. So there is the data. It's got the names it's picked up from the Excel. Next thing I'm going to do is rename the fields so they're a little more compact. So now I've renamed them wavelength and absorbance. Even that might be a little bit long, but okay. And then let's make a plot of this data to see what we're looking at. I'm going to put the absorbance on the Y and the wavelength on the X. So, and I'm using the tilde notation, so it's Y tilde X. And I give it a main, which is the title. I have a \n in there, which gives me a new line character. So I have sort of a 2-line character, one that describes what it is and one that says where I got it. Give credit where credit is due. The label for the x-axis was wavelength. The y-axis was absorbance. So there is that. Okay. Then I'm going to use, I'm going to fit to that form. The form is a height, and then there's a height, a width, a position of the peak. So X is my variable, and H and capital W and LP I've used for my my parameters, my fitting parameters, and H tells me how high the peak is. W, I'm going to just call it the width, but it's the half width at half height. And the LP is the position. So the H is a Y. So the H corresponds to the height. It's going to be a Y. The width and the LP are X's. Okay. And I'm using the NLS. The first argument is putting in the functional form with the X and the appropriate X and Y from our data. And then the second one is our data. So maybe I can turn those around. I think it makes, I'm copying somebody and they put the data second, but it might make more sense to put the data first. And since I'm naming them, I could probably change the order. But here we go. Anyway, this is what I have at this stage. So the data is the peak data. It had fields of absorbance and wavelength, and I'm using absorbance as the Y. So I'm saying Y, and here's my functional form, this Lorentzian form, the height times the width squared, all divided by a big parentheses, the wavelength, which is the x variable, minus the position of the peak. That gets squared plus the width squared. Okay. And then we have the data. And then in the NLS, and the nonlinear least squares method, you give starting points to the parameters. And to get it to give it a chance of fitting and converging pretty well, you should give it a reasonably good starting point. So the height, I said, was, I don't know, 0.4, rough estimate, okay. The position of the peak, 500, okay. The width, 20. So the width is the one that I'm probably off on. The other two are pretty close. And then I'm going to give a summary of the fit. And I'm calling this fit 1 because I'm going to do it all twice just to see if it has much of a difference. So here is my fit. I ran my fit. I run a summary of my fit, so we can see that down here in the console. And here's the H. It's in scientific notation, but it's 0.394. The position of the peak is about 500, and the width is about 50. So that's the parameter that changed somewhat substantially. And it will tell you like how many iterations it took, five iterations, and some measure of how close it fits. Okay. And then I'm extracting from the fit the parameters H, L, P, and W. And so there they are. And then I'm using a curve to fit this formula. And I'm going to plot it from 400 to 800. I'm going to put it in red. I'm going to add it to what I already have. And I'm going to have some width of 2. Okay. And then usually I display the equation, but this I thought was maybe a complicated enough equation that instead I just made a list of the parameters. But I like to put some indication about what actually fits onto my graph. So this is creating a list of parameters, and then that's paste, and then text actually puts it on here. So this is my first fit. And here was my question at this stage. I used the data. I used all the data in this fit. So my data went all the way up into 800, but I'm sort of well past the peak at that stage. I mean, these values are low, but are they throwing off my peak? Is this little bit of deviation here because I included too much data in the tail? Is that throwing off my fit? That was my question. So I thought, well, I can handle that. So here I'm repeating my fit, again, NLS with the absorbance. And now for the data, I'm choosing a subset of my data. I'm choosing my peak data, my data frame that I read from the Excel out on the internet. But I'm only going to go for when the wavelength is less than 580. So up to somewhere in here, I'll say that's the data I really want to fit. I'm not interested in this stuff. And I gave it the same sort of head start. So this is just a fit of all the results, and it didn't change much. I'm going to spit out the values. The width will change a little bit, but it didn't change much else. And I'm just repeating it, extracting all the parameters, drawing the curve. So the blue and the red don't look very different. So that data out there that I was worried, is that dominating my results? It was not. But let's just finish. Oops. Edit, undo. Let's just finish off what we're doing here. So it is different. These values are different. 0.3942, 0.3978, 500.38, 500.52. There was a little bit more difference in the peak. So there was some difference, but not much. This form was not dominated by this data out here, which was good, but worth testing. Okay, and that's what I wanted to show you. Okay, so use open.xlsx to read from Excel. Plot, use the NLS, the nonlinear least squares method. So a form, the data, a starting place, how to extract the parameters from it, how to add the curve, how to display something about all your fitting results. And then if you want to cut some data out of your fit, you can use this subset method. All right, that's what I wanted to show you in this one. Thanks for your attention.